Well, no, but
wait for another 2 or 3 people to come back. Can you see well? Yeah?
yeah.
Otherwise, maybe it's better if they stay.
Yeah, it's okay.
Okay. No, but otherwise you can stay also on the back. This is the ocean session, so.
We were enjoying the ocean.
The ocean is very nice. Okay, so we open this second part of the morning session with Rui, who is going to bring us to the ocean, in addition to showing it to us there on the island prediction system, the Madeira island prediction system, I guess.
Thank you, Nadia. Thank you. I thought about giving you an overview of what we've been doing here in Madeira. Some of the work, so the co-author list was too large to include everyone, so I will be mentioning my co-authors as we go through. This is an effort. I came back from Australia to Madeira to start some research back in 2004. So this is some cumulative effort. It represents a cumulative effort of several interactions, and here I emphasize the ADL, Institute de Luís of the University of Lisbon, that I start working with in these forecasting systems, and then with Ricardo Tomé. CMAR Madeira, which was the first institution that I've helped start to as a delegation of the University of Porto. I was working in the University of Madeira, or with the University of Madeira for 7 years. And right now, I started the Observatório of Madeira. So I'll tell you a bit about the observatory, and then I'll go into the forecasting systems and what questions and inspirations we took from our forecasting experience and transformed that into our research agenda. And then I'll finish it up with some prospects and ongoing work that we have at the moment. So this was my vision when I first came here. This is what I want to do. I think having an island with mountains near the ocean, ideal to study the interface. So we would have, this is a Google plot of Ponta do Pargo, which is the west of the island. So we would have a bunch of radars at the coast measuring. We'd have a bunch of instruments, even some static buoys, and we will have oceanographic phenomena that will be detected, and we could concentrate in sort of a Lagrangian manner a lot of sampling effort into these processes. So this was the vision that started it all. So this was actually the strategy that I followed to try to implement this vision. So let's see how far I went. So the Oceanic Observatory of Madeira is a research unit inside RDT. RDT is our regional agency for research, technology, and innovation. A sort of a mini regional NSF type organism. And since we couldn't host the observatory in any particular institutions, because then they will fight with each other to say, okay, if I put the observatory in the University of Madeira, so this is mine, so the other institutions would not participate. Or if you put it in the Department of Fisheries, they would say, oh, this is mine, then the university would not participate. So I decided, okay, let's go to a neutral client, a neutral host, and try to congregate all the local institutions, which are actually nano institutions that have some sort of activity in ocean sciences, marine sciences. So we did. So the main objective of this regional consortium was cooperation, optimization of resources, implement research and monitoring programs, and in a first instance, try and aggregate data into a common platform. at the moment, we are about 56 researchers, 15 of which PhD. So we inherit some of the researchers that were already doing some research in these institutions, and we contracted about 26, and 8 researchers from independently had their postdocs or PhD work grant proposal accepted by RDT, and they also decided to join us in this effort. So overall we are about 56 researchers, which is not bad for an island of this size. So please consider that Madeira has 250,000 people living, and this is the first big effort we tried to make to join and aggregate everyone. So we've started this effort discussing this in July 2013, and in October 2014, no, January 2014, we've hired the first researchers, and in September 2015, we got infrastructural money, FEDER money, European money, for a project that we put forward. And basically this project aimed at studying or continue the studies and continue the research efforts that these several teams already started in the island. So we have a lot of museums that had a lot of biological collections. We had some local institutions that, for instance, the fisheries and aquaculture, they had some agenda and research interests. So we worked on that, and we built a project to be funded by these infrastructural money, where we developed some biodiversity research, namely creation of a database, study of the impacts of climate change on some species, marine litter, which is very popular these days. But we also had people working on contaminants and impact of contaminants on aquaculture species, as well as trying to diversify the aquaculture production in the island. We had some colleagues also installing telemetry trackers in turtles and tuna fish. So we also wanted to promote the telemetry detection and remote sensing of animals and the monitoring of the behavior of these animals as one aspect of the project. And last but not least, my group of work, where we were interested in hydrodynamic modeling, meteorological modeling, and the study of the mesoscale and sub-mesoscale processes. We joined the team and we put together this project, which I'm the PI. It's about 2 million euros, but it allows us essentially to contract people and inject new blood and new people in these different institutions to try to develop some of these research agendas. So this is about it. So in terms of modeling, this is us, who is now in Spain, but we are mostly here. We have engineers, geographers, mechanical engineers, physical oceanographers, informatics engineer, computing engineers. So I think we are a happy team so far. At least we try. So this is the observatory. I don't know if you have any curiosity, any questions that you want to ask. So this is the institution in itself. It's a bit separate from what I was going to say research-wise. Anybody has any comment?
Yeah. So what about the computational resources? Are they also computational?
No, while I was contracted in Porto, I built high-performance computing infrastructure with about 200 CPU cores, and we maintain that infrastructure. Right now, Rui is participating, is in Spain. He's gone to Spain yesterday or today, and tomorrow there is a conference on the discussion of the supercomputing facilities in Spain. And we are about to join the supercomputing facilities in Vigo. I thought it became a bit not so practical to develop our own supercomputing facilities here, because it would be very limited, be highly difficult to maintain, costly to maintain. So we will developing and investing in our Oporto University infrastructure, but we're moving a lot of these new systems to Vigo, to the Spanish grid. The Spanish grid is a lot more mature. In Portugal, I don't think we have a very mature parallel computing facility yet. So I much rather depend on the Spanish computing system for now. So forecasting, why do we want to do forecasting? So I arrived in Madeira in 2004. So by the time I started to run some models, we had this the February flash floods. So we have recurrent episodes of heavy rains, mudslides, a lot of coastal floods. We have European money that is invested to help build our marinas, which cost 10 million, and then a couple of storms come and they destroyed our marinas. And down the drain goes 10 million euros of investment. So the local government insisted for many years in not having an adequate forecasting system or adequate information, adequate studies to assess whether or not they can construct infrastructure. So I tried to build and convince them that accurate forecasts are absolutely essential. So in 2008, we started publishing our first forecasts. We had a research agenda in our head, but the urgency, the locals wanted, the government wanted were the forecasts. So we used ROMs for our oceanic forecast. We coupled with Mercator, GFS's external forcing, and we used the old good one, MM5, excellent atmospheric model. This was straight in close collaboration with the University of Lisbon, with Ricardo Tomé. And since then, so this is our numerical system. So we use MM5 now. Of course, we upgraded for WRF. We use downscales, system nested grids, two-way nested grids, ROMs, two-way nested grids with Mercator, and occasionally we are also using Swan. We started to publish after evaluating, assessing the quality of our meteorological forecasts. We started to publish this in a simplified manner so that we make people aware that the forecasts were important and they can have access to it in an easy way. So we have this app called Madeira Weather. If you have an Android phone, it's free. If you have an iPhone, you will have to help us pay for the license because they charge 80 euros a year for the license. So we have we compiled satellite images for the last 3 days, high resolution forecasts, but in a very simplified manner. So people wanted to have access to these forecasts, but not in the same way not as technical as we do. And we also put some webcams available in your phone from different sites around the island. One thing that hotels asked us were these forecasts in a very simple manner, so that we can put them in the reception. So if you have noticed in the reception of this hotel, there are some A4s that they publish every day, and this is all automatically generated. It's a PDF automatically generated, so the hotels can pick their location, and their location will be in the first. So 3 days is all I told them to believe. Don't publish more than 3 days, of course. And then you can have all the different counties around the island. Of course, on the website, you can have access to different maps, both for meteorological and oceanic forecasts, streamlines. Here you see the wake, and more technical type of plots. And we also compile a lot of the NOAA data set and plot it ourselves. So for instance, for waves, Wave Watch 3, this is Maria and Lee next to each other. Just a recent plot. And we do it also we do automatically produce 3D visualizations, because we were, from an early time, we were very aware of the interaction of the orography with the incoming trade winds. So for instance, here's an estimate of the total cloud cover over the orography of the island, and you can see that there is a strong interaction. This is the salinity. The Mediterranean water reaches Madeira between 800 and 2,000 meters. So this is the saline water interacting with the island between 800 and 2,000 meters. So this kind of helps us understand some of these processes, and we built some research projects based upon some of the things that we were observing in these 3D plots. Basically, the one thing that you can always see, if you look at satellite images, you see the formation on von Karman vortex streets induced by Madeira. So here you have a visible image of Madeira. Here's your von Karman vortex street. So it goes more than 1,000 kilometers offshore from Madeira. So it's a very strong process, as opposed to the Canary Island vortex streets that they cancel each other out. There's a lot of interaction between these. So they don't reach as far as and as clean as the atmospheric vortexes that are formed here. So you see they can come as far as this is about 900 kilometers offshore from there, and this is not uncommon. This is a very common sight. So we see these a lot. This is courtesy of Oceânico, which is now I think ready. And but you see a lot of this too. So here you have stratification is interacting well with the islands. So you still have von Karman vortex streets and Canaries, but here we are, and this is something that we see. Sometimes we see the vortex streets forming and others not. So one of the first questions research questions was, why is this? What kind of what different regimes cause the generation of von Karman vortex streets? Another issue of interest to us was the generation of a warm water, which is something that Julie is going to talk about later, so I'm not going to expand too much on this. But we do see from satellite image the warming of the leeward side of the island, persistent warming of the leeward side of the island, and it's not just in the summer, but I'll leave that to Julie. We have data to show that, so this is the warm water during one of these episodes. We sampled this with a ship. And here you have some signal. This is potential temperature. You can see that this warm water actually has a strong signal all the way down to 20 meters. And overnight, some of it, due to evaporation, increasing salinity, increasing density, some of it will cascade down. And that's what we think is going on here. So that's some of the stuff that we kind of inspired some of the questions. When we started to evaluate, for instance, our forecasting systems, one thing that we've noticed is that Mercator does not produce the same level of vorticity. So this is a need for us to increase resolution and have something that will actually show known features such as this cyclonic eddies that forms due to the interaction of the incoming currents with the island. So this kind of regional processes were not resolved by general models like Mercator, so we had to increase resolution and in order to do that. Another thing that we've noticed persistently is that our the forecasting system did not pick up the generation of this warm water at the surface. So we really needed a different approach if we wanted to forecast this warm water on the leeward side. So in terms of research, we wanted to continue to understand these different wake regimes, namely vortex shedding, lee waves that form both in the atmosphere and in the ocean. Some vortex shedding forms in the ocean. We wanted also to study the impacts of the atmospheric waves on oceanic waves, how these wind-changing features influence the ocean. This is one of our questions. So how is the transfer of momentum and how is the thermodynamic interaction between the atmosphere and the ocean interplays, and we also wanted to see, okay, once it generates, what keeps these oceanic eddies leeward of the island and for how long, and then I'll talk a bit about what we are doing now, which is a bit more related to the hydrological stuff that we've heard thus far. So, just a reminder, so we have an island in the middle of the ocean, so this is 4,000 meters. So we have a big mountain underwater. And that big mountain interacts with the ocean, with this geophysical flow. You have several regimes, so if you increase rainfalls, you increase shedding frequency, and the same happens in the atmosphere. It's just a different fluid, but they're both fluids. And what seemed to us that was very interesting is actually this interplay between the atmosphere and the ocean. So this is an example of a cyclonic eddy spinning, shedding from there, and this is temperature signal and the chlorophyll signal. So one of the first works is we took, I did this with Pablo Sangra from the Canary Islands, University of Las Palmas, and we took a very simplified schematic channel with realistic fertility of Madeira, and we imposed different fluxes, and we looked at the generation of these waves. And one thing that resulted from this is that, as opposed to the theoretical weights that are often discussed based on the Reynolds number, which are done by a cylinder, but there is a bit different than a cylinder, and you have neighboring islands, and these neighboring islands, they also have smaller wakes, and these smaller wakes interact with the larger wakes, and the shedding frequency and vorticity generated by the main island is very much affected by the presence of the other two islands of the archipelago. So instead of discussing in the literature as it was done thus far on island wakes, we should also consider the discussion of archipelago or multiple island wakes, which is what we tried to do schematically here in these publications. We also took the problem to Hydrolab, so Grenoble. They have about a 12-meter diameter tank. This is me, this is the tank. It's teared down now, they moved to a different location, but it's still in Grenoble. This was a Hydrolab project. And here we've studied with the people from the École Polytechnique, Alex Stegnell, and Haya Lazar, which was a PhD student from Alex. We took this to the lab, Madeira models of Madeira as well as cylinders, and we looked at the stability regime of when the eddies are actually produced, and when anticyclonics are produced, and when anticyclonics are not produced, and why. So we kind of further exploited some of these issues. So this is a rotating tank, so we can mimic the Coriolis effect. And then we will tow our model islands in the tank. The tank was stratified, so we kind of mimic the deep oceanic conditions. And we looked at increase the speed, so increased Reynolds, or we change stratification, or we rotate faster or slower, and that will change the regimes. And we could draw a diagram where things would go more stable or more unstable. So this is one of our ways. In terms of the atmospheric wake, we took into consideration of the discussions in the literature promoted by Etling and Vanda also did some of this work for Hawaii. But basically, so we all know we have a mountain, so if you have an inversion below the top of the mountain, you have a creation of a 2D flow, but if this inversion is above the mountaintop, then you can have a 3D flow. So you have a flow that goes around the mountain, and also you have a flow that goes over the mountain. So this is the kind of regime that we thought might be occurring around there. And one thing that was not discussed in the literature, however, is that apart from changing the height of the mountain in relation to the critical height, in relation to the stratification level, what happened if we would heat up the ocean? If we would heat up the ocean around this mountain, would that change the inversion layer? Would that change the height of the stratification layer? And would that change the regime? So this is one of the questions we found that was not fully discussed in the literature. So apart from the fruit number, we also looked into the bulk Richardson number and looked at these different regimes. And it turns out that if you heat up, so in WRF, you can increase the SST, so you add 5K, or you subtract 5K, or you add 5K. So with the same mountain, you can you can add or subtract 5K from your SST, and that definitely changed the regime. So if you looked at the cut on the leeward side of the islands, you can see that in the control case, you have the hydraulic jump and you have all the stratification keeping this perturbation leeward. And whenever you warm up your sea surface, you generate these lee waves. And actually what you're doing is you're promoting convection, and that convection will work its way through and erode the first stratification layer. And this is a similar cut, but over the ocean. So you see the strong formation of these lee waves. Here I have an animation. This is the control. You can see it's a volume. You can see that like some of the vorticity that is formed. I think this is integrated specific humidity. One of the variables that showed that you have the hydraulic jump, but you don't have strong overflow, persistent overflow, as you have, for instance, in the warm water case. So this is the warm water case. So in the warm water case, we generate this strong internal gravity waves. So this is two different regimes that just by heating up the sea surface, you can promote and something that was not fully discussed in the literature. Another effort we've done with Wanda Grubzik from now NCAR. At that time, she was in the University of Vienna, and one of her PhD students, Joanne's. So I wrote a proposal for the UFAR. UFAR is the European Facility for Airborne Research. So all these airborne platforms that are in Europe, they get funded by European money, transnational money, to promote transnational projects. So people can write small proposals. 3 minutes? Wow, really late. And so we wrote this proposal, and we took an aircraft here, and we did some transects, and we showed the inverse relationship between increase in sea surface temperature, so our warm wake, and the increase in wind. So here, the wind, of course, is stronger in the shear, and the strong wind is much stronger on the edges, on the flanks of the islands, and then you have the warm temperature on the lee side. And this also has had implications on the shedding frequency of these atmospheric vortices. So we had to actually correct for the surface. I think the best comparison will be this, for the surface temperature, in order for the aircraft profiles to mimic the actual model profiles, and that way we also corrected for the shedding frequency in our work. In terms of implications of these atmospheric eddies in the island, so this is in the ocean. I mean, this is some numerical work that I did with Xavier Kovla, the postdoc that worked with me for a few years here in Madeira. So in a nutshell, if you force your oceanic model with a low resolution wind, such as quick spat wind that does not feel the island, does not feel the perturbance, the wind shear perturbation induced by the island. So here you have the wharf. So wharf can actually produce at mid resolution, high resolution, the vorticity, the different vorticities. So this is a half molar. So if you imagine Madeira here, so this is the perturbation induced by the island, whereas for QuickScat, the island, or at least for this data set from QuickScat, the island was not even there. So you see no perturbation. So if you force this with a high resolution wind, what we saw was the generation of these eddies. So there's a transfer of momentum from the atmospheric vorticity into the ocean. Otherwise, we couldn't generate these eddies. But more interesting, this is something that Gia also saw in Hawaii a few years before us. But what not everybody, most people did not see is the fact that we have a wake that is kind of propagates over the ocean for quite a few kilometers. So the eddies get confined to that wake before they actually propagate westward. So due to the Coriolis, you have this westward propagation. But as long as they are confined to that strong shear, strong wind shear, leeward of the island, they were kept more or less propagating southward before they veer westward. So this is something that we've learned. And there is, we figured that this change occurred more or less. This is the wind shear here. This is the trajectory of eddy propagation. So we figured that this is about 2 times the radial deformation number. So we also observed these eddies using gliders, and we found that the heating and cooling. So these atmospheres, I'm over time, yeah. So I'll be fast. So we sampled these eddies, and one interesting aspect of these eddies, it's a smiley. So an anticyclonic is the isopycnicals are supposed to be always like this, but in this eddy you have a cap. So what happened was this eddy stayed in the same position, leeward of Madeira, for 90 days. So during 90 days, it just felt the heating and cooling of the wake. So it capped out. So we cut, it was kind of cut, the surface of the eddy, the top of the eddy was cut, and it formed this different configuration at the surface. And this is it's the same configuration as the mold water eddies that most people talk about. In terms of future work, we're definitely moving into coupled systems in order to study this feedback. We are now trying to compare some of our numerical results with coamps, and we are very much interested in trying to understand the impact of these mesoscale winds on urban areas such as Funchal. So here we are starting to understand, and Julie will show you why mountain and sea breezes are important for us, but they definitely have an impact in these urban areas, pollution events, etc. So we are interested in increasing resolution and be able to solve for these mountain and sea breezes. So we are comparing and evaluating different models, and it looks like different forcings and different model configurations, but it definitely looks like grid resolution is very important. So the LES performs quite well when compared to a mesoscale model. So just to finish, here we just look at the WRF LES study done by Ricardo Faria. The former stuff was done by José Alves, and this is basically showing that we have the formation of sea breezes. So the sea breezes, they came in during the day, only if you have, of course, the surface heat fluxes turned on. So it's very important here. Here you see the sea breezes coming in and penetrating over these valleys. So we cannot disregard the effect of the mountain and the interplay between the mountains and the sea breezes if we want to really generate accurate forecasts for a complex region such as Madeira. Thank you. Sorry.
That's okay. We came all the way here, we want to hear you.
Yes.
So, are there questions? Please.
A really impressive effort. So well done. A more general question, do you want to comment on what the work that you're doing here in Madeira can teach us other parts of the world? So is it specific to island situations, or are there more generic things that we can learn?
No, I think there's a lot of things we can learn from here. For instance, we have a problem with our airport because these down valley winds, they create rotors, and the rotors go over the runway, and that prevents and closes down the airport for a few hours and is damaging for our economy. I was looking into research papers on that. Hong Kong has the same problem, so it's just a scale issue. So I think the fact that we have mountains by the ocean, so you have orographic flows. So if you have a strong interplay of these orographic flows with the ocean, I think we can build a good case study that could improve some model parameterizations or even some modeling approaches that can be used which results can be used and applied to other places in the world. I hope to show that. You had anything in mind?
No, not specific.
Yeah.
I think that's the challenge in a sense, is case studies in one locations or generic.
Yeah.
Again, not just constrained time.
Sure.
Region to the states.
So mountains by the sea, I guess, is the selling point.
I have a question. I mean, you're showing the vortices, and they're very similar to the Hawaiian vortices, and there is also research on fishery importance of this. And you started that work, and how do you plan to? Because that's very difficult.
Yes, yes. I've tried to. The fishery department here is a bit limited to analyze the catch that comes in.
Not here, everywhere.
Everywhere.
Yeah. The catch is
The catch and the management of stocks are done with the catch and eventually bycatch, rarely bycatch, even mostly with the catch that gets in the market. So
That's right.
it's our effort. We did a recent oceanographic campaign, and we invite our partners, the fisheries department, to come and to sample experimentally in different places. They didn't think it was that relevant. So there is a little bit of work to be done. Let's try to include them into our general oceanographic campaigns.
Well, how big is the fishery market here?
It's 1% of the local economy, so it's not significant, but it employs a lot of people. So if you don't have local fisheries, it's artisanal too, so supposedly you don't have a lot of impact. But you see a lot of fish disappearing from the market, so some impact has some impact. The question is whether or not the government is willing to make an effort to, and our colleagues are willing to also go out to sea and take samples and start measures. We don't have a vessel locally, a research vessel, so this is one difficult aspect. When we do have, and this is why, I mean, I hear my colleagues complaining about this for years and years, and when I got a vessel, then they didn't think it was that relevant to come on, so we need to work a bit more.
Thank you. Thank you very much. It's a tough problem, so.
Yeah.
Then now we go to Petros, impact of rain on ocean wave and feedback to the atmosphere.
Hello, everybody. First of all, I would like thanks Rui, Nadia, and Julie for the invitation. I will present the impact of rain on ocean wave evolution and its feedback to the atmosphere. First of all, I will give a very short description of our carbon system, and I will present its responses to the atmosphere and the sea state, comparing against the offline mapping that we had. And I will talk about and its impact on the forecasting, on the overall forecasting, because Nadia wants to hear something like that. Actually, it's this presentation is the last one before the break, the lunch break, so I will try to accelerate my speech. Well, sea interaction, as you probably know, it's a very important field of science because the 75% of the Earth's surface belongs to the ocean. So the synergy of air motions with sea currents and the sea state, the ocean waves, actually modify the momentum fluxes, the sensitive heat fluxes, mass fluxes, even the gas fluxes. and actually affects the release of sea salt from the sea surface to the atmosphere. This was our primary concern, to develop a fully capped atmosphere ocean wave model in order to estimate the impact of the sea salt as a CCN, as a cloud, as a condensation cloud nuclei in the upper troposphere. So especially ocean waves actually determines and modifies the Earth-sea interaction fluxes in terms of the momentum, of heat fluxes, and the turbulent kinetic energy. So on the basis of ocean wave dynamics, medium to high frequency waves actually are primarily responsive to the sea surface roughness and extract energy and momentum from the atmosphere. The modification of momentum, energy, and moisture actually affects the thermodynamics characteristics of the marine atmospheric boundary layer. Moreover, the sea spray plays a key role, as well the white capping, the foam, on the establishment of the marine boundary layer. So there is an urgent need to construct multimodal, multi-scale advanced prediction systems in order to resolve the entire processes, the entire mechanisms on the Earth-sea interfaces. So, although coupling systems are simulating the entire physical processes in a more realistic context, it is not always reflected in a robust and a massive improvement on the forecast key. So we proceeded to develop our CAP model, which is based on the atmospheric component, of course, and the ocean wave component. Those two components are actually communicated through this formulation. This is the estimation of the total roughness length, which consisted of the wave-induced term and the viscous terms. So, at once the atmospheric component estimates the near surface wind speed, then the ocean wave component estimates the well-known Charnock parameter, alpha. In offline coupling, alpha remains constant throughout the simulation. So, in the case of two-way coupling, we have a spatiotemporal variation of the Charnock parameter. Charnock parameter actually is estimated with the wave-induced stress to the total stress, and actually is linked the sea state with the wind driving parameters. So, this is the chemical, hydrological, atmosphere, ocean wave system, chaos, namely chaos, which actually consists of the warp model. We keep the components of hydro and chemistry idle, and we also introduced the one ocean wave model, and those two components are actually communicated through the OASIS couple. These are the Gauss exchanging fields. Almost the entire coupled systems are exchanging the near surface wind fields, and they are getting back the Charnock parameter. We went a little bit further because we're getting back wave age, significant wave height, phase velocity, friction velocity, roughness length. So in our system we have two roughness lengths. The first one estimated by such phase layer parameterization sim of the one model, and the second one from the one model. Do not consider that those two parameters, although they are the same, it's friction velocity or the roughness length, have the same values as they are predicted by WARF and WAM models. We proceeded to prepare some modification in the Monin book of default surface layer parameterization of WARF. We introduced an additional estimation of the channel parameter, now based on the wave age instead of the stress. But in our simulations, we keep the default estimation of the channel parameter as it was proposed by Janssen. Some technicalities regarding the degradation through OASIS. Actually, we defined two more internal communicators in WARF and WAM in order to exchange the fields. It's double. We keep their intracommunicators because in WAM is also a fully parallel system, and all these communicators are under the global communicator of chaos system. What we saw by implementing counting that simulation. So chaos, of course, offer a more realistic representation of the aerodynamic roughness, especially over rough sea surface. So space-time channel variability is mainly affects the high frequencies of wave to the medium one. It means that it mainly affects the tail of the ocean wave spectrum. And the roughness is progressively decreased with the increase of the wave frequencies in the case of swell conditions. And the improvements are more prominent for open sea because the wave spectrum is more sensitive to the wind-generated waves. Two-way coupling actually changes the equilibrium, the budget between the RC, enthalpy, and momentum. We noticed that chaos simulates a more turbulent and deeper marine atmospheric boundary layer, having a weakening effect on the cyclones as well. This energy imbalance delays the cyclone evolution and produces some modifications in the mid-sea level pressure, actually increase the mid-sea level pressure. The troposphere also responses to this surface forcing. Actually, we noticed responses up to the 7 kilometers, not only on the wind fields or the temperature, even in the water vapor mixture ratio and the relative humidity as well. How all these things are translate in forecast scale. Yes, we noticed the robust statistical improvement up to 24% over sea and over 5% over the land. These are experiments, simulations that we made over the Mediterranean Sea in high impact medcates in extreme weather events. So, as you probably know, the wind is the fundamental factor that affects the Earth-sea interaction processes. But is the only one? The answer is no. It's also rain. And rain actually is not incorporated in the CAD systems so far. Rain actually has the effect of damping especially the high frequencies of the ocean waves, and produces a more turbulent near-surface atmospheric marine boundary layer. So, rainfall affects the wave generation and determines the sea surface roughness by enhancing both vertical and horizontal stresses, depending on the way that the rainfall impacts the sea surface. In the case of wave sea state, the collision between raindrops and sea surface waves lead in the decrease of the significant wave height, and decrease of the white cap as well. In Country State, the momentum flux from the raindrops to the sea surface, leading the generation of the capillary waves, the well-known ripples. It's like this. There are a few papers in the literature that deal with this topic. So, in general, rain is damping the significant wave height. Rain actually is damping mostly the high frequency, in a range from the high frequencies to the medium frequencies ocean waves. Kumar also observed that damping at low wind occurs when the horizontal momentum is relatively lower, much lower, compared to the vertical. So it assumes that you have a vertical, like this, drop of precipitation. Cavalieri, in a recent research in JGR, if I remember well, proposed that actually rain attenuates high-frequency waves, but the sea surface roughness and the white capping is actually decreasing as increasing the wind speed. Young waves are more affected by the external forces such as the raindrop, and on the other hand, under swell conditions, the swell waves are not so sensitive to the precipitation. So we prepared an experiment adding this term to the surface layer parametrization scheme of Monino-Bukov for the estimation of the roughness length. This is the impact of rain, which actually related with from the drop diameter, the kinematic viscosity of water, the rain intensity, and the terminal velocity of the rain. This is positive parameter is added with the estimation of the roughness length. And we tested in a well-known high-impact hurricane, Sandy. Sandy, as you probably know, developed at the end of October 2012 over Caribbean Sea, like there. And then it actually enhanced by the intrusion of a fast propagating trough from the northwest and the existence of the anticyclonic system at the center of the Atlantic Ocean. So we implemented chaos in two sensitivity tests. The first one is incorporating rain in the estimation of the roughness length, and the second one, the control one, was avoiding to incorporate the impact of rain. We ran chaos on 10 kilometers horizontal resolution, and 0.1 resolution is the relative resolution of 1. These are the domains. And the exchange rate between the two systems are 10 millions. It means that there is an exchange ratio between the atmospheric component and the ocean wave component 1 to 10. And these are the results. Here is the rain, 3-hourly accumulated rain of Sandy. In the case of rain, rain means that it's the simulation incorporating the impact of rain in the estimation of roughness length, overlaid by the mean sea level pressure. So this is the response of the roughness length. Here we have an extended area where the rain bands are more intense around the eye of Sandy, And this is the difference between the rain experiment and no rain experiment. This means that you have, of course, a large increase of the surface roughness in the areas that you have very strong precipitation. This is actually reflected in the estimation of the wind speed. Here you have differences, reduces of the wind speed around these areas. Of course, you have some kind of patches, red and blue patches. It means that the system, sandy, is not always, is not only reduced its density, but also delays, because you have more friction in the case of the rain. And this actually reflected in a reduce of the significant wave height that reaches 2 meters offshore of Florida. We proceeded to check the roughness length as they estimated by rain experiment in red color and no rain experiment in blue color as a function of the friction velocity. We noticed that actually the medium velocities are mostly contributed to the enhanced of the roughness length, because these are this is the spectrum of the wind that mostly related with the rain intensity. We also prepared this plot, which is the ratio of the bulk transfer momentum of enthalpy to the momentum, which is a ratio that characterizes the hurricane intensity. We noticed that in the case of rain experiment, again, the medium wind speeds are mostly contributed to weaken the sandy here. This mainly can be attributed that there is that the kinetic energy loss, that sandy lost kinetic energy in a more fast way that gains heat. This is the evaluation of the track of sandy. The magenta line stands for the observed track, and the red one with the rain experiment, and the blue one with the non-rain experiment. These are the mean sea level pressures that we noticed in every date and time step which are there. Of course, the rain experiment improved not only the track here of sandy, but also its mean sea level pressure, which is quite closer to the observed. We evaluated against 23 buoys over the Atlantic Ocean there, with JSON 1 and 2 satellite retrievals, and for over 100 surface weather stations located at the East Coast and Puerto Rico and Cuba. These are the scatter plots for the buoys, the left hand, and the satellite for the wind speed. We do know that WRF model systematically overestimates the near surface wind speed. Actually, rain improves, actually reduce this overestimation, and of course, reduce the rhythm square error as well for the wind speed. It is also reflected the significant wave height as well. It also reduced the overestimation of the significant wave height in the case of sandy, and improved the rhythm square error as well. Summarizing, the rain experiment improved the significant wave height, the significant wave height in the case of sandy, and improved the rhythm square error as well. these are we got reduced for the root mean square error for the wave approaching the 11% here in the case of comparison of comparing against buoys, and 9% in comparison against satellite retrievals. But in all cases, the incorporation of rain on the estimation of roughness length offers a significant improvement of the forecast scheme. We also noticed that we have improvement in the forecast scheme over the land. So it improves the mean sea level pressure against it reduces the underestimation here, and actually improve and the precipitation pattern actually it reduces the overestimation. This is the bias score for various precipitation threshold. It actually reduces the overestimation of precipitation for the medium to high precipitation thresholds. And that's it. So this is the impact of rain in a limited area of water, which is very limited, but okay, just imagine that something like that happens over the ocean in the case of very intense phenomena such as like hurricanes, cyclones, whatever.
Is that hail?
Yeah, it's hail. Yeah, it's hail. it's not bowling.
Okay, so thank you for being on time. We have time for questions. Yes, please.
So I was wondering, your formulation that you changed the drag in the atmosphere, did you do the same thing for the wave model?
No, we implemented this only in the water model, in the atmospheric model.
But presumably, you should have the same effect on the wave generation source.
If we do this on the one model, we will get a very large drag. So we'll again, you mean to incorporate this term in the
Because
surface?
the resource term is actually in the wave model is also related to drag.
Yes, but
So for the Janssen scheme is wave age, right? So presumably
Janssen scheme is not wave age dependent. No, it's
it's
dependent
the
on the
stress. It's
on the stress.
the stress,
Yeah.
the stress is that's kind of wave age dependent. So if you, the rain damp, you
Yep.
know, damp the high, you know, the frequency of the wave, change the frequency of the wave.
Yeah.
Right, so you have the shift of the energy spectrum, so you think that the source generation from the wind,
Yeah.
you should have some effect there.
Actually, our first experiments were to add this term, because Kumar also, in his paper, add this term to the wave model. But we got, as an output, a huge reduction of the wave. And we couldn't evaluate why it went wrong there. I suspect that one roughness length, not is not correct, but it's not at least the same, at the same order with the atmospheric. And the first experiments will compare the roughness length and the U star estimated by the work model and the roughness length in the U star estimated by the ocean wave model. And we noticed that there are almost 2 magnitudes of order differences. So here is a little bit trial and error. We added there, and of course this is very important.
Yes, yeah, I agree. So just kind of comment that our system that when we started the work about a decade ago, we found was kind of inconsistent and a couple of different models together. The air seemed to play
It is not a matter just to put two models to play together.
Exactly, so.
It's not technicality.
That's why I have this question, is that when you do something for the atmosphere model, you also need to consider the influence to the, not just the wave model, and that has indirect feedback back to the oceans.
Of course. Of course.
All three of them depend on us.
Okay, it's kind of average, so the impact on SST, which you are not putting in because you're not using notional.
No.
You think you should also include them in chaos?
Yes, we're currently working to implement NEMO model in this.
Okay.
I'm so optimistic. In 1.5 years, we'll incorporate in the ocean circulation component in chaos. It could be very interesting, but of course, very, very difficult because, the fluxes are more intense in this case. You have a 3D model, just to count another 3D model. And although we noticed a lot of, we faced a lot of problems to count a simple 2D simple ocean wave model with an atmospheric model, we assumed that we faced against more problems to put NEMO in the game and to make all these components to talk each other. And don't forget chemistry, because our first concern it's in wharf chemistry.
Yeah.
Because our first concern was to estimate in a more accurate way the sources of sea salt in order to propagate them into the atmosphere and to act as CCNs. This is our target, but we're getting some steps.
I might say on the last point that there are several oceanographic papers that show the importance of precipitation on temperature variation of the surface ocean. There are several parameterization. George Miller in the past did many. We also have new data sets that are showing the importance of the stratification of precipitation in that. So I think that it will be, even without coupling fully all of them, the precipitation, we have neglected it. The effect of temperature, the effect of precipitation on ocean temperature has been neglected completely up to now in all models that I know of, except maybe some local ones. So it is certainly something to be added also for the ocean part, the carbon. And I'm going back to instead a very important issue that maybe is tomorrow also another issue to bring back to the attention, is this consideration of the different meaning or the different values of U star across the RC interface, which are really very important issues to be solved in the next 10 years, I guess, in order to have better forecasting models, both of hurricanes or ocean waves or currents. So maybe this is,
Yeah, Nadia is of course, very important, but it is a matter to homogenize, the different components that we're putting in the CAP systems.
Yeah.
It's not a matter just to take one model for the atmosphere, take one model for the ocean, and together and let them play. It's not a matter of that. You have to be there, the interface, to check always the fluxes, to check always the budget of energy. And in order in order to prepare, in order to develop a sustainable model, in order to provide at least more realistic results. Okay, so, and closing, I don't know if I have just 1 minute. This formulation, it is obtained from laboratory experiment. There is no field experiment in order to evaluate, in order to assess the real impact of rain on the ocean. Well, so it's nice, good for fall.
I was wondering, so this Z0 is used also for the heat flux calculation, right?
No, it is for the momentum, but changing the momentum also affects the heat flux. We noticed,
You notice
of
different.
course.
Heat fluxes. But so you have a separate Z0 for heat fluxes.
No, there's not.
It's the same one.
It's the same. Yeah.
So you did check the impact it had on the heat fluxes? Did you find it realistic?
Well, there is no way to evaluate the fluxes because we have not measurements in the fluxes.
Let's say compared to an analysis of fluxes, the DOA flux analysis.
Yes. Yes. We checked in the initial stages of developing chaos the fluxes with analysis and some kind of. I think that one student of mine checked with satellite data. I don't know if there is any kind of satellite retrievals with surface fluxes, but I don't remember. No, there's not something like that.
Yeah, are you use the OA flux that put up by the telescope?
Yeah,
So they have that.
I'm not sure if this is the data, but okay. He prepared some kind of very good comparison between the fluxes that we estimate here and the analysis fluxes, and we noticed that we are quite good, quite in good agreement. But it is very difficult to say something uncertain that okay, it is correct or it's not correct. We can check it by the results if you are getting improvements in the precipitation, in the track of the system, in the vertical profile of the atmosphere or whatever. It means that okay, and the fluxes are correct, more or less.
So thank you very much. And now Rumi will tell us what we do with the.
Yeah. Okay, so you probably haven't failed to notice we're going to take an hour for lunch, so we will be eating until 2:30. We're going to push then everything back half an hour and then move the final talk, Cheryl and Williams talk till tomorrow. That's better timing and also better continuity subject-wise. So Cheryl and will get the third talk tomorrow. So we should be back on schedule after those small adjustments. So we're eating lunch back